Hi, everyone. Welcome to this week's Robotics Colloquium. We are very excited to have today's speaker, Professor Aaron Johnson from CMU. Aaron is an assistant professor in the Mechanical Engineering Department, and he holds appointments with electrical and computer engineering and the Robotics Institute. He directs the Robomechanics Lab, where his research group is focused on studying the mechanics of robot behaviors and how to design intelligent interactions between a robot and its environment. His group conducts research on various aspects in robotics, some of which include design and control, motion planning, and state estimation on legged robots and wheeled mobile robots. Some of the applications to which his research caters to are in the field of search and rescue operations, planetary exploration, manufacturing, and personal assistance. The theme for his research group is to build robots that can go anywhere in the world. And Aaron has received several recognitions for his contribution to the research community, which includes NSF Career Award and Young Investigator Award from Army Research Office. Thanks, Aaron, for taking time to virtually visit us. We are all excited to have you here and listen to your talk. Please take over the Zoom floor.
Great, thanks, Karthik, for having me and for that introduction. I think you saved me 2 or 3 slides at the beginning here. So, as you mentioned, my name is Aaron Johnson. I'm an assistant professor at Carnegie Mellon, and yeah, my lab is interested in building robots that can go anywhere in the world. So we want to take robots out of the warehouse, out of the factory, and into more unstructured environments. And whether that's rocky, hilly, broken terrain that you'd find in natural environments, or stairs and sidewalks and curbs and clutter in human environments, the big difference is that we can't control the lighting, we can't polish the floor to be perfectly flat. And we're not going to sort of know the friction. We're not going to know exactly which rocks are loose and all of these things. So here's some of the applications that we're thinking about. Things like planetary exploration. Here's a Mars rover type vehicle running a test where we're using the wheels to dig in the sand instead of having another tool to do that. We also have a big project right now on environmental monitoring. So sending robots out to collect soil samples and look for contaminants in the soil. And what are some of the challenges that come from these kinds of environments? So on the locomotion side, here's sort of a blooper reel of some of the robots in my lab playing in the park behind campus. And what I want you to notice in all of these examples is that the failure really starts from unexpected contact with the world, either bumping into something you didn't think you were going to bump into, or trying to put your foot down and not having something there to support it. So here this robot is just trying to walk around, and it doesn't know that its leg is hooked on this ivy as it's moving. Or here it's bumping into this log that it thought it could step over, but it can't. And so that it's running its shins into the log. Of course, the flip side is if you think that you're going to make contact and don't, that can be just as bad, if not worse. So for instance, this video here, the robot's going to take a few steps, and then it puts its foot down, and there's not really as much support as it thinks in it, and it rolls over. And this challenge of sort of unexpected contact with the world is not just a robotics problem. So here's a YouTube video of a New York City subway station where over time the stairs have sort of settled so that one's just slightly higher than the others. And looking at the stairs, you don't really notice a difference. But here you can see everyone, as they're sort of swinging their leg up to the next step, bumps their toes against the lip of the stair, and they start to trip. And again, it's this sort of unexpected contact with the environment that causes these issues. There's also a big problem in manipulation. So it's not just locomotion. Here's a blooper reel from a paper we had picking up small objects, where all of the failures can be traced to either bumping into the object early, or having friction that didn't match what the model said, or just sort of failing to bump into the object when you were trying to push it. And so this motivates the sort of 2 key challenges that we think about in my lab of contact and uncertainty. And the challenge with contact is really the discontinuous nature of contact. If you've got your foot 1 millimeter above the ground, then you get no contact force. And then as soon as you touch, you can have very large contact forces. And so this inherent discontinuity makes it very challenging to operate with. And then uncertainty. Again, we're not going to have a perfect model of the environment that we're working in, and it's not going to be, we can't control it. And so we sort of accept uncertainty as a given and work on designs and algorithms that embrace that uncertainty. And then, of course, these two things play into each other, where if you have a discontinuous process like contact, where a small difference in state makes a huge difference in your contact conditions, then uncertainty plays a big role in that. So in today's talk, I've pulled out two recent projects from the lab. The first on the more robot design side, looking at tails, and the second on the control side, looking at state estimation with contact. So I'll start with this sort of cheetah-inspired tail project. And this was with students Joe Norby, Junjang Lee, and Cameron Selby, and then our good collaborator, Amir Patel from the University of Cape Town, South Africa. And the observation in this project was that tails are ubiquitous in nature. I mean, here's a selection of animals from a recent zoo trip. And we see a wide range of forms and functions in these tails, from this tiny little one on the armadillo, to these huge tails on the lemur and the monkey. And animals seem to be using tails for all sorts of things, either as balance or attacking or defensive postures, as well as communication. I mean, the lemur's tails, the reason you stripe your tail black and white in such a high contrast is so that it's easy for your friends to see you when you're trying to get their attention. So in particular, in this project, we were looking at cheetah tails. So here are some of the videos that Amir's collected in his experiments of a cheetah chasing around like a cat toy on a lure. And we can see that the tails are moving around a lot as they're running. And it seems like in particular, they use their tails for sort of starting, stopping, and turning, which we call maybe sort of agility behaviors. And the tail seems to help them balance and improve that agility. So what do we want tails for in robotics? So specifically in this project, we're thinking about how do we recover from foot slip, right? If we're going to have uncertainty in contact conditions, we know that our feet are going to slip. That's a given. And one of the problems when your foot falls off a ledge is not only is that probably not what you planned, but now you can't apply any correcting forces with that leg, right? So you thought you'd be pushing on the leg, you're not, so you have to do something to correct, but you don't have any control authority out of that leg. So it's sort of an especially tricky problem there. And this is something that a lot of animals do use their tails for. So again, here's the cheetah that's sort of sliding around on the dirt, and you can see the tail flipping around to try and keep it balanced. And also on the left here, this is a lizard running, and at some point you'll see its back right leg on this big rock right about here, slips off. And right when that happens, it kicks the tail up so that it doesn't end up tumbling and head first into the ground. We'd like to be able to get this kind of slip and tripping recovery in our robots. So there's actually been a fair amount of prior work on robotic tails. This goes back to the 90s with Garth Seglin and Mark Rabert. This is the Uniroom. But really, it's been in about the last 10 years that there's been a sort of an explosion. And this is honestly a pretty small selection, there's many others, of robots trying to use tails and trying to get some of the advantages that we see in nature. And one of the things I want you to notice about all of these different tails I have up here is that they pretty much have the same design. So almost all of the prior robotic tails that are out there are basically a long stick with a big mass at the end. And I'll call this type of tail an inertial tail. The idea here is that we want to have as large an inertia as possible, and then we'll get equal and opposite reaction. So if we move that large inertia, we get an equal and opposite reaction on our body, and we can apply a corrective moment to the body of the robot. And this is pretty similar to how lizards in particular use their tails dynamically, where they have big, heavy tails. A cheetah tail is only about 2% of the body mass. And most of that mass is at the base, unlike those robotic tails. And so the inertia is really small, especially if you think about a cheetah. It's this big, muscular animal, and it kind of has this foofy little tail at the back. If you're just getting equal and opposite reaction, it's just not enough force to actually to matter at all. But what they do have is a lot of fur on their tail. And you can particularly see this in this video where Amir's taped some pink tape on the robot to make tracking easier, and he sort of pushed down the fur on the near the tip of the tail. The tail itself is actually very skinny, especially out of the tip, but there's really long fur that has a very high aerodynamic drag. So the question is, can aerodynamic drag really play a significant role in the dynamics of cheetahs as well as in our robots? So to try and answer this question, we calculate what we'll call tail effectiveness. And this is sort of how big a correction to the body's angle can we get for a given rotation of the tail. And inertial tails are very easy to model, and they're very directly proportional to the inertia of the tail. So if you double the inertia of the tail, you get twice the effectiveness. Right? And this just comes from this equal and opposite reaction. With aerodynamic forces, the forces are a little bit more complicated. They scale with velocity squared as well as length to the fourth. And so we can't have a closed form solution. Instead, we have to integrate it over a particular trajectory. But from our sort of aerodynamic equation here, we see that if we wanted to build a really effective aerodynamic tail, we would want to maximize the drag coefficient, the speed from that velocity squared, as well as the length for length to the fourth. And so as a robot builder, I think I know how to make things long. That's pretty straightforward. If we want to maximize the speed, let's just gun it. Let's see how fast this motor can go and try and take advantage of that velocity squared. But we kind of got stuck on how to maximize the drag coefficient. So here's some pictures from some of the different tails that we've tested. Everything I know about aerodynamics, which is not much, is mostly about how to minimize drag. And here we've got a problem where we want to maximize drag. So we tried a bunch of different designs. We did some wind tunnel tests and some CFD. We settled for now on this tail you see in the upper right. That's sort of a half circle of thin plastic that we're pulling along. And this is pretty good. It's pretty high drag coefficient, but I don't think that we've really nailed this question of how to maximize drag. So that's something that we're sort of still looking into here. One of the issues with artificial fur is that it's mostly very soft, because that's what people buy fake fur for. But then it just sort of all folds over and you don't actually get very high drag. Anyway, so with this tail, let's now look at what kinds of behaviors and what kinds of dynamics we can get out of these aerodynamic tails. So from the model here, I'm showing this is 3 different tail lengths going across. And then in blue is the inertial contribution. So this scales exactly with the x-axis, which is the tail inertia. And then in red, we're showing the aerodynamic contribution. So how much of the body correction comes from adding in the aerodynamic forces. And a few things we can pull out of this model. The first is that we really can get a pretty large effectiveness from the aerodynamic contribution. So I'll start just with this middle figure. If you're looking at on the left side of that middle figure, we can get about a tail effectiveness of about 0.4, which would be the equivalent of a very heavy tail, where the inertia was about 0.4 of the whole system. So we can really get pretty significant contributions from this aerodynamics. And the other interesting thing that came out of this model that I wasn't expecting is that you actually, if you have an aerodynamic tail, you can optimize its performance by minimizing the inertia. So this is in contrast to the inertial tails, where the more mass, the better, right? You get a larger effectiveness. With the aerodynamic tails, if you have a heavier tail, you can't accelerate it to the same speed. F equals ma. So if we have a heavier tail, our acceleration is lower, and that velocity squared term is really pretty dominant. And so we see that there's this dichotomy. If you're building an inertial tail, you want to make it heavier. But if you're building an aerodynamic tail, you actually want to make it lighter. And so there's this sort of dip in between where you have to decide which side you're going to go on. So the model says we can get pretty significant effectiveness, pretty large. effects on the actual robot body. What does this look like on a robot? So here, this is, I think, a pretty mean robot test. So what we've done is we've taken the robot, we've hung it up by a string, face first, about a half meter above the ground. So you can imagine if we didn't have a tail, this would fall like a brick and bust up the front of the robot. Instead, here with this tail, it's able to reorient the body 90 degrees and land on its feet safely. And so the tail in this video is a 110-gram tail moving a 7.3 kilogram robot. So inertially, we've shown here from the model, if we just move that inertia, we'd get about a 30-something degree rotation on the body. But because it has a very high drag coefficient, we can actually get a full 90-degree rotation and make it all the way to land on our feet. This is great. This is like sort of the high performance. What's the most effect we can get out of a tail? Hopefully, being tied up by a string a half meter above the ground isn't a common scenario for the robot. So what's maybe a more practical application? And thinking about back to the cheetahs in these kinds of agility behaviors, starting, stopping, and turning. Here, this is showing forward acceleration. Can we jump faster? Can we launch into a running speed faster if we use a tail? And what we found was that we can actually accelerate 12% faster than if we didn't have a tail at all, which is exciting because normally if we put extra mass on a robot, it runs slower. And while the tail is very light, it still has a motor, it still has motor controller and wires. So we are adding a decent chunk of mass on the back of this robot, but it's able to sort of more than make up for its own weight and actually accelerate much faster into a running behavior or a jump. So with these tails, we found that yes, aerodynamics really can play a big role, which I think at first I was skeptical of because the cheetah is a pretty big animal, and you think of drag as being pretty small at the scales we're talking about. And this is especially true for long, lightweight, and high drag tails. And then we can actually translate this into pretty significant effects on the dynamics of our robot. And so one of the things that we're working on now is we've got a 2 degree of freedom version of this tail, and we're doing experiments, I think actually this week, out in the park to try and use the tail for these kinds of recovery behaviors on the robot. And moving forward, I think we still haven't really maximized the drag coefficient. I think there's more we can do with microstructure and artificial fur type materials to get even more effective and maybe more biologically inspired tail rather than this giant sail that's in this picture. All right, so that's sort of an example of the sort of bio-inspired design side of the lab. And in part 2 here, I'm going to change gears a little bit and talk controls and look into this question of common filtering for hybrid dynamical systems. So the students on this project were Nathan Kong, Joe Payne, and George Council, postdoc. So motivation for part 2. Here's an example of a robot running a tailed behavior. Again, this is using the same, as we were sort of developing some of the behaviors with the tails. This behavior was generated with trajectory optimization, and then we're tracking it online as it's running. And it's working pretty well. So this is using that acceleration behavior into a running gait. This is slowed down, I think, 25% or something. And this works pretty well. And so we thought we had pretty good state estimation and tracking on the robot. And then we moved just slightly faster and generated a slightly different behavior with the tail and the legs. And the online tracking completely failed. So as it's going here, if you looked at the trajectories, they're very similar. We're not really asking for something all that different. And the robot isn't able to sort of track it directly. If you look at the sort of at the joint level data, the legs are actually staying pretty close to where we wanted them to be. In fact, you can kind of see them go through the motions as if they were on the ground, as if it was sort of running along happily. It's just that the feet are just above the ground. And so when they go to push really hard, we don't get any acceleration on the body. And so again, this comes back to uncertainty in contact conditions and the sort of challenge of state estimation. So in the second half of the talk, we're trying to answer the question of how can we better estimate our system state, including the body, position, and orientation and velocities under changing contact conditions as we're running them. And so the approach that I'll present today is looking at common filtering on hybrid dynamical systems. And just to sort of parse out some of the jargon here, so common filtering is the optimal linear state estimate based on noisy measurements. So we're going to take in noisy measurements and try and come up with the best estimate of our system state. And then by hybrid dynamical systems, here I mean hybrid as in both continuous and discrete components of state. And in particular, our discrete state will be the contact modes. So whether a foot is on the ground or in the air. All right, let's start with sort of a quick crash course on common filtering. So many of you probably already are familiar with common filtering, but just to get everyone on the same page and to get our terminology straight, what is common filtering? So what we want to do is we want to estimate our system state, and we're going to represent that state as a mean and a probability distribution around that mean. So this dot would be our mean estimate at time k, and we have some probability distribution and common filtering that's a Gaussian around that. And this probability distribution says this is where we think our state may lie with different probabilities. In common filtering, there's two steps. The first step is the prediction step. So as we move forward in time, if we take our model of our dynamics, we can move that prediction forward. We know what the velocity is, what the acceleration is. So we know where we think we should go at the next time step. But as we do that, our uncertainty will grow over time. All right, until we take a measurement, we'll become less and less certain about where we are. Then at some point, we get a sensor measurement. Let's say we see this bright yellow star in the corner. And based on what our sensor reading is, that leads to some probability distribution of likely states that would have led to that sensor measurement. And so in the second part of common filtering, we will update our prediction, the a posteriori step, where we take our prior estimate and this sensor estimate and come up with the optimal combination of the two. So our uncertainty is going to reduce because now we are more sure about where we are. And the state estimate will change a little bit because of that sensor measurement. All right, so that's common filtering in 60 seconds. What happens if we have contact? So if there's an impact event while in our dynamics. So in terms of the continuous time, so before we have an impact, the way that we update our state based on our dynamics and our covariance is updated with the Jacobian of the dynamics. So this A matrix is the linearization of our dynamics at that time. And we use that to propagate our covariance forward in the prediction state, in the prediction step. For the discrete mode, meaning our contact state, when we have an impact event, we'll have some model of that impact process. So it could be plastic impact, elastic impact, whatever our, we'll call reset map is. We can update our mean, our state with the reset map from our pre-impact to our post-impact state. And so the first thing we thought was, what if we use the Jacobian of the reset map to propagate the covariance, right? In continuous time, we use the Jacobian of our dynamics to update the covariance. And so for these discrete updates, we might use the Jacobian of the reset map to update that covariance. So to see how this might work, here I'm showing a very simple and I think quite soothing hybrid system. I like this animation that my student made here. So what we have here is two hybrid modes. So the discrete state is either left or right. Our continuous state is also two-dimensional, x, y. We have constant dynamics in each mode. So the flow is just over and down a little bit when we're in the left mode, and over and up a little bit when we're in the right mode. The guard, meaning the surface where we switch modes, is linear. It's just x equals 0. It's that black line. And then our reset map, meaning that impact law, is just identity. So there's no jump in velocity or state in this model. And we're not going to put any process noise in. So as we're moving along, you can see before we get to the switching surface, the covariance isn't growing or shrinking at all. Everything's just moving with constant velocity. So at the time of impact, if we were using the Jacobian of the reset map is identity. So its Jacobian is an identity matrix. And so that would say that the covariance for the system shouldn't change at the moment of transition. But we can see that the probability distribution at the beginning and the probability distribution at the end have very different shapes. The covariance is quite different here. And so it turns out that the Jacobian of the reset map does not capture how the uncertainty changes through these kinds of hybrid transitions. Instead, we have to use something called the saltation matrix. So the saltation matrix is the variational update to our dynamics. So if you have a variation, meaning a displacement from some nominal point, the saltation matrix maps that displacement before the reset to that variation after the reset map to first order. And so what does this matrix look like? Well, the first thing is that it looks like the Jacobian of the reset map. That really is most of the story in terms of how things propagate through the reset function. And then there's this complicated other term that I'm not going to get into the details, but there's a correction term that factors in the dynamics in each mode, as well as that guard surface and the reset map itself. And so this saltation matrix is what we're going to use to propagate our uncertainty. So if instead of using the Jacobian of the reset map, if we propagate the covariance with the saltation matrix, here in this picture, so red is our initial covariance. And if we went through constant flow, identity reset map, constant flow, we would expect the covariance to be unchanged. So that's this red circle, which would be the same shape as the first red circle. And instead, if we map that covariance with the saltation matrix, we get the yellow dashed line, which lines up exactly with this black oval, which is the actual final covariance. So this saltation matrix gets us a very accurate propagation of covariance through reset maps. Even if we have nonlinear and more complicated systems, this is still the update for the covariance matrix. How does this fit into our common filtering, our state estimation problem? So here, when our continuous prediction, when we're not at an impact time, stays the same as a regular common filter. But when we have a discrete update, meaning an impact, again, our state is propagated with the reset map, but then the covariance is propagated with this saltation matrix. All right, and so this I've written out the prediction step, the first part of common filtering. For the update step, it's sort of a similar story. So what does this look like if we sort of run this common filter with this saltation matrix? So the first results I'll show are for this two-mode sort of blue dot example I showed before. And I would focus on the bottom here. This is the error over time for this trial that I'm showing in the upper right. And so in red is if we use the Jacobian, the reset map. In blue is the saltation matrix, and then as black is a large particle filter. I think this is a 1,000 particle filter, which is a lot of particles for a very simple system here. And the things to note, first, before we get to that hybrid transition, all of these filters work about the same. And that's because this is just a smooth system up until that point. But then after that transition, after that impact, the Jacobian of the reset does much worse than the saltation or particle filter methods. So we're able to get much better prediction. Again, we haven't changed how we move the state. The nominal model is the same, but by updating the covariance to be the correct covariance for our system, then we get better estimates as we get more sensor measurements after that transition. The other thing to note real quick is if you look very closely around the time of impact, the saltation matrix's version, the SKF, is doing slightly worse than the particle filter right around that transition. And that's because the common filter assumes that all of the uncertainty is propagated in one time step. So if you have a large amount of uncertainty or very small time steps, you would imagine there'll be several steps where a significant amount of your belief is on each side of that transition. And so that's not captured in this kind of local filtering approach. So this is a very simple system, constant flow, identity reset. What if we go to a more complicated model? So here, this is like a hopping robot model, higher degrees of freedom, nonlinear. We added a change of basis at reset, and then we're going through multiple transitions. And again, I would focus on the bottom, the error plots, in particular in this Y direction. And so this blue SKF is doing much better than the red Jacobian of the reset version in that direction. But it's interesting to note that in the other directions, the two filters seem to work about the same. And this is because the saltation matrix is actually a rank 1 update to the Jacobian of the reset map. Remember, the first term in saltation matrix was Jacobian of reset map, which is what this red filter is using. And so that's really capturing most of the story. The difference is in the direction of the guard. So in this case, the impact happens in the Y direction in this model. And so we see that the main difference is in our tracking performance in that Y direction. So the takeaways from this common filtering section are that the saltation matrix allows us to propagate uncertainty through hybrid reset maps. And in particular, we can now use this to do common filtering for these kinds of hybrid systems. One of the things we're working on now is extensions that allow us to maintain some belief in multiple different modes. So when we sort of get halfway across that transition, can we maintain there's a 50-50 shot, we're on each side of this line. And then the other direction coming out of this work is applying similar ideas to trajectory optimization. So this figure here at the bottom, this is a paper that's under review, but this is doing ILQR, but playing similar tricks to this common filtering idea and generating trajectories that undergo multiple transitions without having to specify what the sort of contact sequence is ahead of time. So I have a lot of concluding thoughts here at the end. I think we still have plenty of time. Just to sort of quickly summarize the main points from today, I think that the key challenges in my lab, as well as in robotics in general, are contact, and in particular, the discontinuous nature of contact as we go around and are interacting with the world, and uncertainty, and embracing the fact that we won't have perfect models and we can't have exact state estimation, and trying to survive with that uncertainty. I covered sort of two different areas, one on more the design side, one on more the control side, but they're sort of both really focused on how do we handle contact, how do we handle uncertainty and in these robots that are sort of moving in unstructured environments. There's a lot of other projects going on in the lab that I don't have time to get into too much, but real quickly, we're working on building very simple walking machines. In particular, we want them to be simple so that we can make them very small, with the ultimate goal of building something the size of a Lego that can actually walk on its own. We're also thinking about higher level motion planning and control for legged robots that are able to sort of jump over obstacles, climb stairs, and do different sort of dynamic behaviors. I also work very closely with the manipulation lab. We have a joint project building direct drive hands. And the advantage there is that they're very transparent. So they're very back drivable. In this video, we haven't told it how high the table is or exactly what the shape of the object is. And we just smack the hand into the table as fast as we can. And we don't break the fingers and we don't break the table because the linkage design is very transparent to the contact uncertainty. And finally, we have a poster coming up in L4DC on learning rough terrain dynamics, and in particular focused on trying to leverage a large amount of simulation data with a small amount of more expensive robot data in order to learn these kinds of challenging dynamics driving over rough terrain. But I wanted to leave, yeah, we're still good on time. I want to leave some time to talk about a new project that I have with Sam Burden's lab here at UW. And so I thought the best way to introduce this project, it's about multi-behavioral robot design, is I'm going to read you a children's book called The Mixed Up Chameleon by Eric Carle. You probably know him from The Very Hungry Caterpillar. So this is a story about a chameleon who's bored. I'm going to skip the first few pages. I'll catch you up. A chameleon who's bored with his daily activities goes to the zoo and is so inspired by all of the animals there, he wants to take advantage, have the same sort of capabilities that they all have. All right, and so he says, the chameleon thought, how slow I am, how small I am, how slow, how weak. I wish I could be big and strong like a polar bear. And the chameleon's wish came true. So now he's bigger, he's got this white hair like the polar bear. But was it happy? No. I wish I could be handsome like a flamingo. So now we've got some beautiful flamingo wings and legs. I wish I could be smart like a fox. Apparently, foxes are smart because of their tail. But anyway, he's got a fox tail now. I wish I could swim like a fish. So we've added in some flippers so we can swim like a fish. I wish I could run like a deer. Again, I'm not really sure what the antlers have to do with running, but he's got some antlers from a deer now. I wish I could see things far away like a giraffe. So he's got a long giraffe neck now and can see far away. I wish I could hide in a shell like a turtle. We've got a nice shell there so he can protect himself. I wish I could be strong like an elephant. Wish I could be funny like a seal. Apparently the flippers are the funniest part of the seal. And I wish I could be like people. And it looks like the defining characteristics of people are hats and umbrellas. Just then a fly flew by. The chameleon was very hungry, but the chameleon was very mixed up. It was a little of this and a little of that, and it couldn't catch the fly. I wish I could be myself. The chameleon's wish came true, and it caught the fly. So why did I tell you this story? If I go back to this slide, this is a pretty, intentionally ridiculous looking composite animal here. But I argue this is actually the way that we design robots often when we're thinking about what we want the robot to do. So I'll pick on myself. Here, this is the environmental monitoring robot that we built this past year. And we said, we need a mobile base. So we got this tracked platform. We need to be able to get over curbs. So we've added these flippers that help us get over curbs and obstacles. We need to be able to see the environment. So we have a mast that goes up and has a LiDAR and cameras and stuff. We need to be able to break up the dirt to sample it. So we added a rototiller on the back with a high-speed motor. We need to be able to collect the samples. So we've got an arm with a scooper at the end to scoop up the dirt. And then we need to be able to bring that back to be analyzed. So we have some sample collection buckets on the back. And what we end up with is this kind of monstrosity of a robot here. And it's not just us. So here's a bunch of popular mobile manipulation robots. So these are robots that want to do at least two things. They all need to move. They all need to manipulate things. And I can literally draw a line between the mobile base and the manipulator arm that they used, where it's pretty clear that a different team, or maybe even a different company, designed the mobile base, and then someone bolted on an arm on top of that robot. So how do we do better than this? How can we design a robot that is good at multiple different things without just every time we have a new behavior, we strap on a new appendage? So this is an NSF NRI award with Sam Burton here at UW, my former postdoc George Council, as well as students Joey and Amber from Sam's lab. So we're just getting started, but we're making some good progress on coming up with more synergistic robot designs that should come out soon. Before I wrap up, I wanted to say a few things about supporting diversity in robotics. It's, it shouldn't be a surprise to know that the demographics of the robotics community look nothing like the demographics of the rest of the country or the world. And I think it's very important for all of us to think about what can we do what actions can we take to actually improve this? And because it's clear that if we don't actually take some actions, then the situation's not going to change itself. So I have some suggestions here. I encourage you to join a networking or advocacy organization. So there's Black in Robotics, was formed last summer. There's Women in Robotics. There's a nice new webpage now. There's Black in Engineering, Black in Computing, and there's other ones out there. These are all sort of relatively recent organizations. I encourage you to read, cite, invite, mentor, collaborate with a diverse set of researchers. So we built this Black in Robotics reading list. There's also a US Women in Robotics list and other similar lists to help you find if you're saying to yourself, well, I would love to do that, but I don't know who I would collaborate with. I encourage you to go check out these suggestions. And then lastly, spend some time to learn more. So there's this Spectrum article on supporting Black scholars in robotics. There's these great action item lists from Black in Engineering and Black in Computing that you can look through and think about, what actions can you take as an individual researcher, as a lab, as well as us as the robotics community to make it a more diverse and inclusive space. And so that I'll wrap up and happily take any questions. Thank you.
Thanks, Aaron, for the stimulating talk. So I'll open it up to the audience if they have any questions. I have a question about the design of the tail. Like, it's probably very simple one. So I saw that you were actually experimenting on different furs and to figure out which actually gives you the aerodynamic drag. But the end design that I saw seems to be like fairly simple. So I wanted to know like what made you choose the non-furry, like simple one?
Yeah, so we started looking at fur because we were looking at cheetah tails. All in the fur we could find was very soft. That's the kind of fur that we typically sell. And you can even see in this video on the top where we're just spinning it around. Again, this video is slowed down. It's moving pretty fast here. All the fur, if it's very soft, just sort of folds over, and then you just have a smooth cylinder. And a smooth cylinder actually is a pretty low coefficient of drag. The cheetah fur is actually pretty stiff, so it stays up sort of even even if the air is moving by at a high velocity. So I think it's sort of a materials question. I think there's also a lot we could do with 3D printing microstructures and these kinds of things to have something that's stiff but has a sort of higher drag coefficient than we can get with these materials. Again, I have never taken an aerodynamics class. I come from the sort of electrical engineering side and control side, but we were working with someone in my department on the sort of CFD side and doing these sort of wind tunnel tests. And it's an interesting problem in that almost always you want to minimize drag. And there's been a lot written about how to minimize drag. Here we want to maximize drag, and with the caveat also that it's got to be pretty lightweight, because again, the heavier the tail is, we can't accelerate it as fast, and there's this velocity squared term that's pretty dominant. So finding a lightweight but high drag material is pretty challenging. Yeah.
So I have a number of questions I could ask, but the number one burning hole in my brain is, so inertia is good for inertial tail and bad for an aerodynamic tail. So it sounds to me like there's a trade-off to be had. But if I'm not mistaken, you didn't. I'm sure you've been thinking about it. But if I'm not, sorry, did you talk about it? Like, with the what would the best tail design be with some inertia and some aerodynamics, or where what does that trade space look like?
Yeah, so it's bimodal is the answer. So this black is the sort of total effectiveness, and if you have what I'll call an aerodynamic tail, you want to be to the left here. Oh, can you see my cursor here? If you're to the left of this dip, then you want to go lighter to maximize your aerodynamic drag to get up to higher speeds and get higher aerodynamic drag. If you're to the right of this little dip, then you want to increase your mass, and you don't actually care the speed at which you move the tail. It's just about moving that inertia a certain distance, and you'll get the equal and opposite reaction. So there's not like a happy medium. The like in between is actually worse than one or the other. I sort of assumed it would be more of a continuum, or that yes, take advantage of the aerodynamics, but you still might as well throw as much mass on there as you can, right? To take advantage of the inertial effects as well. But that's not the case. You kind of have to choose. And so it ends up being sort of bimodal here.
I have a exciting way to connect the two parts of your talk. So there's reasons to believe that animals using moving limbs might also be using those because of the sensory opportunities those afford. Do you think there's a role for that in robotics, or does the fact that we can use an IMU just kind of trump that, or what are your thoughts?
No, definitely. We think a lot about what I would call proprioception in the lab. And I'll skip ahead. You kind of see it in this video in the lower left with this hand of we're using our fingers as sensors. There's no contact sensor. There's no force torque sensor here. We're just in this case, the fingers are still, but the arm is moving. But we're moving the fingers through the world. We don't know where the table is. So here in a moment, it'll show we've sort of stacked up different books to get different height tables. We're running the same code in all three of these, and we're using the fingers as the sensors. And this is, I think a very good way to go. Lots of people use tactile sensors. Those are either not sensitive enough, or they break all the time. There's always new tactile sensors coming out, so maybe they'll get there eventually. But I think of the fingers or the legs in the legged robots, or the wheels and the wheeled robots as being free sensors. They're already interacting with the thing that we're trying to measure, and so let's get as much proprioceptive information as we can out of them. And so we have this IROS paper in the fall was on contact localization for this hand as well as some of the legged robots, figuring out not just did you hit something, but where on your limb did you make contact, completely proprioceptively. Yeah.
Yeah, you can picture when you make contact with the ground, that tail flop all over the place.
Yeah.
Yeah.
Yeah, definitely. And animals drag their tail in the ground all the time in a way that, in robotics, we're often sort of afraid to bump into things, right? We've got our wheels or our feet, and that can touch the ground. But if the body bumps into the ground, or the manipulator arm or your camera head, that touches the ground, that's usually considered failure. But that's not the way the animals work. They're dragging things through the dirt all the time. And so one, I think we need to be designing our systems to be okay. If we're going to run in challenging environments, we know we're going to bump into the ground. And two, we might as well do that intentionally. Yeah, definitely.
Hey, Aaron, thanks for the great talk. I was wondering if you could comment on the tails in relation to joint limits, in particular the trade-off between the inertial approach and the velocity, the aerodynamic approach. It seems like there would be some advantage to the aerodynamic approach because if you hit that joint limit, you're not dumping that inertia back into the body. But can you comment on that?
Yeah, let's see. I think I took that video out. That's one of the big problems with inertial tails. So you dump a ton of torque to accelerate this huge inertia, and you actually got to do a lot of work to stop that inertia. So the first test I did with inertial tails, we didn't really think about the stopping. We just worried about seeing how far we could move the tail. And it smacked into the robot so hard it ripped the motor mount off. And sparks were flying and ripped the whole tail off the back of the robot. So stopping the inertia is a huge cost with inertial tails. You can do it with your motor, in which case it's sort of an energetic cost. You can do it with the body, in which case it's sort of how strong did you make the tail and the body so that you can have that impact and survive it. And so that's one big advantage of the aerodynamic tails that I didn't get into is that they're very light. So they come and with the high drag, they come to rest pretty quickly when you stop pushing on them. Yeah. The other thing with, you mentioned sort of joint limits. So inertial tails, we have this effectiveness. I'll go back to here. So the effectiveness is really the change in angle of your body is proportional to the change in angle of the relative angle to your tail. So if you have a joint limit on how far you can move the tail, that exactly specifies how far you can rotate the body. It's a little bit less clear with aerodynamics because it depends on how fast you can accelerate the tail. And if you can accelerate to a higher speed faster, then with the same range of motion, you can get a higher effectiveness. Yeah, so you can end up sort of breaking that, that rigid limit on how far you can go in a single stroke.
One other thought I had on that was you're showing the use of the tail for reorientation using the motor that's controlling the tail. But when in thinking about the cheetah, it's getting a lot of velocity from its body movement and not just the movement of the tail itself. So that could be another advantage.
Yeah, certainly if you're running very fast in the forward direction, or if you think about the drop test, if you're falling very quickly, and you can sort of put your tail out into that airstream that's going by anyway, that's just going to increase. Here we just have it as a theta dot, but this is really the velocity of your tail relative to the airstream. So if you're moving very quickly, that only helps here, as long as you're sort of pushing in the right direction. Gives you a much higher effective velocity. Yeah, our robots don't run at whatever 70 miles an hour that a cheetah can, and so it's a little bit less of a advantage in the robot. But as we start to run faster, that'll certainly play in. Yeah.
I was just wondering, like in the future iterations of the research, do you see that the tail design could be more articulated, maybe using soft materials and stuff to, I don't know, if that is actually useful, or what are your thoughts on that?
Yeah, I mean, certainly you look at these animal tails, the armadillos may be pretty close to 1 degree of freedom, but the rest of them are all very soft and flexible. Some of that is what they're working with. It's much harder and much more dangerous to have very rigid things in biology. In terms of the dynamics of either inertial or aerodynamic effect, any amount of compliance is sort of slowing you down. Actually, if I show in the drop test results here, the actual, they're in red, lags behind the sort of model in black, primarily we think from flex. If you watch this, the tail is, we tried to make it rigid, but we also wanted it to be light. So there's a good amount of flex in the tail. And so you can see that in the lag in this plot. So it'll slow down your dynamics. You sort of can't respond as quickly, but I think it'll be an advantage overall in that right now we wouldn't really want to smack this tail into the ground because it's very brittle. And so having something softer, that's sort of more compatible with sort of dragging through the rocks would make a better system overall.
If I can, the last thing I want to do is, Aaron, can you put up that second to last slide again about diversity in robotics? I mean, I just want to give you accolades for putting, not only including this slide, taking time out of your research to talk to us all about this and give us these resources, but also just, I know that you were being humble in not putting your name next to all of the things on this slide that you were actively a part of, but there's a number of them, and it's just very impressive, the work that you've done in this community on this issue. And partly selfishly, I wanted you to bring up the slide again so I could screen cap it. I was away from my computer when it was first up there, but now I have it. So
yes.
Thank you.
Yeah, I'll leave this up. And again, after this talk, don't go to my website and look at my papers. Go to this reading list and find someone that a researcher you didn't know about that was working in the same area as you.
Let's thank Aaron once more for his time and for the fantastic talk. Yay. Thanks, Aaron.